This is Suba Nagar, Kovilpatti, located at 9.168 degrees north, 77.868 degrees east. This region sits on the black cotton soil belt of Tamil Nadu, supporting agriculture for centuries. But beneath this fertile ground lies an engineering challenge we are here to investigate. The sample you see here is inorganic clay, dark grey to black in color, sticky when wet and hard when dry. This is typical black cotton soil, known geotechnically as expansive clay. Today, we are characterizing this soil to understand why it creates problems for construction. Specific is this hydrometer analysis, liquid limit, and plastic. Here is the goal. First, from feeling solution, our soil is clearly fine grained. That is, it is sticky, smooth texture, no visible sand particles. For this type, hydrometer analysis is the correct choice because it measures clay and silt particles smaller than 75 microns. Seed analysis wouldn't work here since it's designed for poor soils with sand and gravel retained on the seed. Second and third, liquid limit and plastic limit. These Atterberg limits are mandatory for IS 198 classification of fine grained soils. The liquid limit will tell us the compressibility class, whether our soil is low, medium, or high compressibility. The plastic limit will help us calculate the plasticity index, which determines if we are dealing with clay or silt and whether it plots above or below the A line on the plasticity chart. We excluded relative density because that's only for cohesionless sands, not for cohesive clay. We excluded proper compaction because it's for finding optimum moisture for compaction, not for classification purposes. By choosing exactly these three texts, we follow the IS code, top based resources on unnecessary procedures.
Hydrometer analysis determines particle size. We have mixed up to 50 grams of soil in water. It determines the larger particles settles faster and the clay particles remains suspended. So our result is 72.8% as clay and 27.2% as silt. And so there is no sand is present. So the soil is fine graded and the high contaminant remains, say that the soil is swells well and shrinks as such.
Liquid limit states that determines when soil changes from plastic to liquid state. We use gas-granted tool with proofing tool. We tested at different moisture contents 200 blows, 148 blows, and down to 5 blows. We plotted water content versus log of blows. From the graph, liquid limit is 58%. Since this is greater than 50%, our soil has high compressibility. Flow index is 14.4, showing rapid consistency change with water content. This high liquid limit confirms the soil will become soft and unstable when saturated.
Plastic limit is the moisture content where soil contains when rolled into 3 threads. We perform thread rolling test 3 times. Average plastic limit is 27.95%. This measures water content drops below 28%. These soils become brittle and crack. This explains the ground cracks we see in Suba Nagar during summer.
We present our findings. Look at this sample. Notice the dark color and fine texture. This is not ordinary soil. Let me explain what our test is revealed. Hydrometer analysis showed us the particle composition. As you see on this chart, we have 72.8% clay particles, that is anything which is smaller than 0.002 mm, and some 27.2% silt. and zero sand. This 72.8% clay content is critical because it explains why the soil behaves the way it does. Now, Atterberg limits. Our liquid limit is 58%. On the classification chart here, anything above 50% falls in the high compressibility zone. The plastic limit is 27.95%. Now, watch this calculation. Plasticity index equals liquid limit minus plastic limit. CA minus 27.95 gives us 30.05%. So then, when we plot these values, 58% on the x-axis and 30.05% on the y-axis, this point falls here, above the A line and in the high compressibility zone. So, final classification is CH, which is inorganic clay of high compressibility. So, as per IS 1498-1970, what does CH mean practically? So, high compressibility means high settlement potential. So, inorganic means no organic content that would decompose. Clay means cohesive soil with swelling characteristics. The activity number of 0.41 indicates inactive clay minerals, but the high plasticity index of 13% means significant volume change potential. 8 to 12% shrink-swell behavior is observed. This soil will expand when wet, exerting pressure upward and crack when dry, causing differential settlement. Any structure built without addressing this will face the cracks and tilting be documented in Suba Nagar.
To summarize graphically, our soil plots firmly in a CH zone. The particle distribution shows complete dominance of clay fraction. The 30% plasticity index puts us in a very high plasticity category. The engineering implications are clear. The soil requires ground improvement before any construction. The numbers don't lie. The liquid limit above 50% means the danger for shallow foundation. Thank you.
I am now showing you the reality of construction in Suba Nagar. Look at these photos. What you see are isolated pad footings, individual concrete pits evacuated for each column, concrete by beams ground levels. Photo 1 shows multiple column foundation with reinforcement cages and spaced about 3 to 4 meters apart. Photo 2 shows these footings are all only about 1 to 1.5 meters depth. This is now near depth enough for CH soil. The active zone for black cotton soils wheeling extends 2.5 to 3 meters depth. These footings sit right in the danger zone. Photo 3 shows the compound wall built on a random rubble masonry sitting directly on untreated soil. No CNS layer, no stabilization. Photo 4 shows a wooden formwork for plinth beams. These beams will transfer load, but when the soil squeezes and sinks seasonally, differential settlements will crack these beams and walls above them. The problem is in the footing type, pad footing and can work, but they are built directly on untreated expensive clay without ground improvement. That's why we see the failures.
So, what actually happens when you build on this soil without treatment? Let me show you what we found right here in Suba Nagar. Look at this first photo. See these granite slabs. They are cracked right where they meet the wall. Now, granite is strong, but look at the gap forming. The soil underneath couldn't take the weight. It just settled because our high compressibility soil has very low bearing capacity. And here, in this photo, this is inside a house. See that gap between the floor and the wall. That's not poor construction. That's the floor sinking down while the wall stays up. The soil shrank in the dry season and pulled the floor away. Then look at the road. See how it's all bumpy and cracked. Every monsoon, this soil swells up, pushing the road up and then dries and sinks again. Happens every year. So these cracks aren't because of bad materials. The granite is fine, concrete is fine, it's the soil. Our high compressibility soil classification predicted exactly this. high compressibility, low bearing capacity, and seasonal swelling. So that's what happens right there.
Now the solution for CH soil, we recommend 6 provision technique. First, lime stabilization. Mix 4 to 6% quick lime by weight with the top 30% of soil. The lime clay reaction reduce plasticity from 30% to 15 to 20%, making it not expensive. Cost effective for roads and single story buildings. Second, cement stabilization. For heavy foundation, 5 to 8% cement content can achieve unconfined compressive strength above 2 MPa, making the soil suitable for load bearing. Third, CNS layer. Replace 1 to 1.5 meter of cohesive non-swelling soil between the black cotton soil and foundation. This creates a better buffer zone, isolating the structures from volume changes below. Fourth, preloading with sand grains. For large structures, apply 1.5 times the design load for 3 to 6 months before construction. Install 300 mm diameter sand grains at 2.5 meters spacing to accelerate water escape. This reduces post construction settlement by 70%. Geogrid. Fifth one, geogrid reinforcement. Use biaxial geogrid at the base of pavement to distribute loads and prevent reflective cracking from underlying soil movements. Sixth, moisture control. Mostly important, mean perimeter drainage and waterproofing to prevent seasonal moisture variation, the root cause of seizing. Implementing these band on structures weight and importance can prevent the failures we showed you. This is difference between the reactive repair and proactive engineering.